I don't have to. So yeah, hello everyone. Welcome to the third and last seminar of this year. It's a pleasure to have David Ridout today, who will talk to us about brand new work, as far as I understand. The paper appeared this week. So we're all curious to hear what's going on.
It is brand new as it appeared, but the work's actually more than 2 years old, as I shall explain. It's just my basic premise with not getting things done in a reasonable fashion. So let me share my screen. So I'm afraid I haven't had time to make pretty slides, so I've just written some stuff up on my lecturing software, and I hope that's okay. So this work was originally for a very strong student by the name of Will Stewart that I had a few years back. So he was my master's student for 2 years, and then he went to apply for PhDs all around the world. And as you can imagine, being a very strong student, he ended up getting a PhD in Texas Austin. And so he's doing a PhD with Dan Freed and Sam Raskin. That's a great outcome for him. Now, what happened was, of course, he finished at the end of the year and then had 9 months before he would have a chance of starting at most places. And so, therefore, he sort of enrolled at Melbourne as a PhD student, but always with the intention that as soon as he got something better, he would leave. So he did get something better and he did leave. I was essentially trying to come up with something that he could do in 6 to 9 months, which would teach him a lot about various bits and pieces, but most importantly would have a chance of getting him a publication. So a colleague of mine suggested this thing called the Nappi-Witten model, which, to be honest, I hadn't really looked at too closely in the past. And so this was essentially his project. And so what happened was that he completed pretty much everything that I'm going to tell you today, modulo a few minor details. And then being stubborn, I tried to push it further and further, and realized that there was something a little subtle going on, which I didn't really understand. So after debating this with collaborators for a significant amount of time, I eventually bit the bullet, gave up, and said, all right, let's write up the results that Will originally got and submit it to the archive. So that's the paper which just came out. I think it was last week, or maybe it was this week. It's Will's first paper, so I hope that he's fairly proud of it, and I hope that he's not too upset by the fact that it took me almost 2 years to okay it for submission. Such is life. All right, so I think everybody here is pretty much an expert in everything. So let me just start with some very brief background info. So I'm a conformal field theorist, so I will be talking about conformal field theory. As you all know, conformal field theory is the best part of string theory. And maybe that's not quite an honest statement, but from my point of view, it certainly is. In many respects, conformal field theory and string theory are often almost the same thing. And it's probably the case that, the heyday of conformal field theory back in the 80s and early 90s was really being pushed along because of the rapid advances being made in string theory at the time. So I'm going to talk about a bunch of things here, and maybe some of it will be controversial, but this first part, I think definitely not. So I've just drawn a little picture here to try to remind you of things that hopefully you already know. I think we've seen things like this before. If we look at the closed string world sheet, and so here I'm just taking it to be a cylinder, but really you could take it, you could compactify it to make it a Riemann sphere, or you could make it a torus or a homogeneous surface if you like, corresponding to loops in the string, so interactions if you prefer. So this is the simplest case where we just have a very boring topology, but we have a spatial coordinate which is periodic, and we have our time coordinate, which is not. And this gets mapped into some target spacetime. And so I've drawn 3 arrows for dimensions, but of course this could be 26 or 10 or 507, who cares? It's just some target space. And so this is, string theory in a nutshell. But conformal field theory, generally what we do is we consider the theory pulled back to this string world sheet. And we make a coordinate change to take advantage of the fact that conformal transformations are very naturally expressed in terms of complex structure. And so we make a coordinate change to map the cylinder, or if you prefer, the twice punctured Riemann sphere, onto the complex plane, or if you prefer, either the compactified complex plane or the once punctured complex plane at the origin. So the angular spatial coordinate gets mapped, the periodic spatial coordinate on the cylinder gets mapped to the angular coordinate in the complex plane, and our good friend time gets mapped to the radial coordinate. And so conformal field theory mostly takes place over here. So maybe I'll skip that for a sec. One popular approach to string theory, according to me, is first of all, understand the conformal field theory. So that's my favorite part of the whole process. And then if you are able to understand the conformal field theory in sufficient detail, then you can impose all the remaining constraints which make the string theory consistent. So there are example Virasoro constraints or gauge constraints, those type of things. Right, and so from that way you can take a CFT spectrum, a space of states, and you can cut it down to size to get the actual physical states that the string can realize. All right, so I want to make these maybe slightly contentious claim that the very first step, understanding the conformal field theory, has a few parallel communities out there, certainly in the literature, but also I think among different people. So here's another cartoon, which is an attempt to draw some of the communities who are interested in conformal field theory and string theory. And I've kind of put a rough timeline on the left here. So you can see starting from the 80s right down to close to present day. And I've also separated just in terms of, theoretical physics versus pure mathematics. And I think mathematical physics is this whole gamut in between, this line running between the two. So back in the 80s, most people were studying rational conformal field theory. Very exciting and wonderful, as hopefully you all agree. And there's not so much of that happening now, but I guess there's still many, many applications of this. I guess what I want to say is that in the late 80s, mathematicians who were maybe inspired by this or maybe working independently on problems of their own invented things which ended up being axiomatized and called vertex operator algebras. And so in a very strong sense, the study of vertex operator algebras tells you an awful lot about conformal field theories. So that's a useful thing. Mathematicians can be useful at times, that's true. I'm cat fighting outside, how exciting. I would like to just indicate bridges between these various communities with literal, oh, how exciting. That could be a problem. I hope it's not my cat. Yeah. So anyway, I'd like to indicate a bridge between the vertex operator algebra and rational CFT communities. But I've kind of rubbed out some of this bridge because I think it's actually not a very good bridge. So I think they were basically not talking very well to each other. They were possibly interested in what each other was doing, but not to the extent where they would really figure it out properly. And so we see that certainly at the time in the early literature, there was a lot of exciting things being done by physicists, which were not exactly being replicated. Certainly mathematicians tended to be interested in very different questions at that time. All right, but this is perhaps a contentious proposal, and certainly I wasn't around at the time, so probably shouldn't be so annoying. In any case, a bit later on, let's say mid-90s, early to mid-90s, physicists discovered what are called now logarithmic conformal field theories. So these are not rational. They're not rational in quite a special way, and I've drawn a little bridge to indicate that a lot of the initial work about logarithmic CFT was really initiated by physicists who were studying versions of rational CFT which failed some of the standard properties. And these found applications, so it was a natural thing to look at. You'll see down here I put a little bridge between the vertex operator algebras and logarithmic CFTs, because I think it's been true that in the last 10 years, this has really become much more mainstream with the mathematical community. And so I think there's a lot of mathematicians now who are interested in logarithmic CFTs. I'll talk a little bit about what that means later. The last community I want to talk about is somewhat ephemerically entitled non-rational CFT. But that's not to say it's basically everything which is not here. I mean, these logarithmic CFTs are also non-rational. But nevertheless, that seems to be the moniker that they've adopted for themselves. And here, non-rational CFT really seems, I'll try to explain roughly what that means a bit later as well, but here it seems to be a separate community which is looking specifically at examples which arise in certain applications, including string theory. So there's large communities of physicists who are working on non-rational conformal field theory. There is, of course, some obvious bridges between this and rational CFT. I think it's probably fair to say that you need to learn a little bit about rational CFT before you go on to study non-rational CFT. But the point I want to make here is that there's, as far as I'm aware, very little work which tries to relate the logarithmic and the non-rational communities. They seem to be developing in parallel, and they don't seem to have too much to do with one another yet. So one reason why I was interested in studying this Nappi-Witten model is that it's an example of a non-rational CFT which has received much attention in the literature, but which I think many of us secretly believe should be a logarithmic CFT. In fact, many of us believe that logarithmic CFTs and the non-rational CFTs are almost the same thing. Not exactly, but almost. So it's interesting to sort of get a sense for what's going on here.
May I interrupt for one question?
Yeah.
Is there a bridge between vertex operator algebras and non-rational CFTs?
I think there's not too much at the moment, but I'm not an expert in non-rational CFTs. So I honestly couldn't say. Honestly don't know. My suspicion is not much. From what I know of the vertex operator algebra community, they're quite scared of non-rational conformal field theories. It's very hard to prove theorems about these things.
Thanks.
But that's just my opinion. All right, so let's go back to getting onto this example at hand. So if you read string theory textbooks, you're hit with the bosonic string, where the target space is just d copies of R, so some nice like real space. And sometimes you'll be talking about compactifications. So when Peter was talking about T-duality, he was talking about target space compactification. So for example, you might take one of your dimensions and wrap it up into a circle. And so here we might take n of our d dimensions and wrap them up into an n torus. Right, so the space or space-time itself is still flat in an appropriate sense, but this is still relatively easy to analyze, and by easy I mean, Johanna can give you an entire subject on it and then leave you wanting more and more and more. So that's nice. Of course, we know that space isn't necessarily flat, and so it makes a lot of sense to look at toy models in which the flatness is traded for something, a little bit non-flat, but maybe not totally chaotically difficult to deal with. So one of the first examples of non-flat spaces and spacetimes which were studied were called Wess-Zumino-Witten models. So Witten introduced these, gets his name attached to a lot of things, funnily enough. And here the target space is a Lie group, or if you want to make your life a bit harder, a Lie supergroup. So this Nappi-Witten model, which again was introduced by Witten and Nappi, this is an example of a Wess-Zumino-Witten model. And in this case, the particular Lie group, which is acting as our target space, is four-dimensional. So for those of you who want to do string theory, you'll realize that this is a non-critical string theory. But the Lie group is four-dimensional, and it amounts to a slight extension of the well-known Heisenberg group, if you know about that. And interestingly, it is a solvable Lie group. And this makes it decidedly non-textbook. So the CFT textbooks tend to talk about Wess-Zumino-Witten models, but when they do, they immediately start by saying, suppose that your group is simple, then blah, 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 blah. So of course you can generalize that to semi-simple Lie groups without too much hassle. And from there you can get to reductive Lie groups, that's okay. But solvable ones don't seem to enter the picture. So this is quite a different beast from the Wess-Zumino-Witten models that you find in the textbooks. All right, so what does this algebra look like? It's actually kind of familiar. So it's four-dimensional. And so I'm going to just choose a basis, which I call E, F, I, and J. I and J are basically like a Cartan subalgebra. So in particular, they commute. I and J commute. E and F are acting as raising and lowering operators in the sense that, well, I is actually central, so it commutes with everything. But J is kind of like your J3 if you do SU2 kind of commutation relations. So J with E gives you E, and J with F gives you minus F. Right, so E and F, you can think of them as being raising, lowering, or ladder operators, or annihilation, creation operators. And if you look at this algebra very closely, you'll see that this is exactly the algebra that you get when you study the quantized harmonic oscillator in your first quantum mechanics course. So in fact, E and F are the, what do you call them, the A and A dagger, the annihilation and creation operators. I is the identity, so it's H bar, if you like, it's a constant. And J then, what's J? Anybody? I'll see if anybody's actually listening or whether they're all off watching YouTube. Seems nobody's listening. All right. So J is, of course, the Hamiltonian or the number operator. So this is a Lie algebra that everybody knows extremely well, and nice to see it cropping up in the Nappi-Witten model. So just to be clear, the Nappi-Witten model has the corresponding Lie group. This is a non-compact Lie group as its target space. So this is just the corresponding complexification of the corresponding Lie algebra. So I said before that this is a solvable Lie group. The Lie algebra is also solvable. This means that the killing form is degenerate, which means that the standard Sugawara construction for the energy momentum tensor is not going to work. You have to be able to invert the killing form in order to apply the standard Sugawara construction. Same for computing the quadratic Casimir. It's the same calculation. Okay, but it turns out that this.
Sorry, I'm interrupt with a very naive, stupid question. Is it easy to see that this being solvable implies that the killing form is degenerate?
Well, so there's a theorem, which is that a Lie algebra is semi-simple if and only if the killing form is non-degenerate.
Okay. All right.
I think it's called the Cartan second criterion or something like that.
Okay.
But yeah.
Okay, thank you.
No worries. All right, so we don't have the killing form in the sense that we can't use the killing form to get an energy momentum tensor. And you remember from CFT that the energy momentum tensor is where the conformal invariance lives. So in order to get our conformal field theory, we have to construct an energy momentum tensor in some other way. And so the nice thing about this algebra is that you can swap the killing form for some other nice bilinear form. And so here we want it to be invariant. So we want it to have to behave itself with respect to the commutation relations. It should be symmetric. That's more of a convenience. And more importantly, it should be non-degenerate. And so it turns out that there's actually a two-parameter family. There are lots of them. So you don't just have to deal with the dodgy killing form. You've got all these other ones just lying around crying out to be used. So with any of those, you can apply a generalized Sugawara construction. And so you can get your conformal field theory. It turns out that all of these bilinear forms, when you look at the real Lie algebra, have signature 3-1. So that suggests that you're going to be working with a Lorentzian target space, which kind of makes sense, right? We've got 4 dimensions, we've got Lorentzian signature. You can see why Nappi and Witten thought that this might be a useful model to look at. All right, now if we've got heaps and heaps of non-degenerate bilinear forms, doesn't that mean we get lots and lots of different energy momentum tensors, and so lots of different types of conformal field theory? The answer, luckily, is no, because there's also a bunch of automorphisms of this algebra. And when you take those into account, you can see that all of these different invariant forms actually end up giving you exactly the same, well, chiral algebra. So you get the same conformal structures. Nothing special about that. And so chiral algebra here is the physics term. Mathematicians will call this thing a vertex operator algebra. Hopefully that's reasonable. All right, these automorphisms can also be used to show that when you do the usual affinization procedure, the level of the affinization can be tuned to 1. So this is familiar from other string theories like the free boson or the free fermionic string. Both of these, they don't really have a level. You can always just redefine your generators so that the level is 1. So we usually do. Similarly, if you look at the string theory on the supergroup most closely related to the Nappi-Witten model, this is GL11, which Thomas, I believe, has done quite a lot of work on in the past. It also doesn't really have a level. You can just tune it to be 1. So this is relatively simple and gives you hope that the string theory that you're looking at here is not too different from these flat space models like the free bosonic and fermionic strings. And indeed, one thing which hopefully we remember from our first string theory course, that the central charge of a bosonic string is just the number of dimensions of the target space. And so that turns out to be true for the Nappi-Witten model as well. We have a 4-dimensional target space, and the central charge is exactly 4. So again, it's not really that different so far. All right, so the claim, and this is borne out in the original paper, is that this particular target space, so this Lie group, describes strings which are propagating in the background of a monochromatic plane wave. So just a single frequency. So there's a plane wave, and I guess you can probably think of that as being a gravitational wave of a single frequency. But I might be, I've forgotten how to be a physicist in the last 10 years, so maybe that's not entirely accurate. And essentially, to show this, what Nappi and Witten do is they parameterize our H4 group, plug that parameterization into the Wess-Zumino-Witten action, so the standard thing that you do, and then you look at it, fiddle about with it, and extract out the effective metric. So you identify a kinetic term, figure out what the metric is. There's a B field, which is not too complicated. There's a dilaton, which I think is constant. But you extract the metric and then say, have I seen that metric before? Ah, yes, it's the metric corresponding to the background where I just have a plane wave. So that's kind of nice. So it's basically saying, look, it's like flat space, except that you have this background wave. So you can ask what's happening to the strings, what's happening to your string theory when you have this particular type of background. Not so different from a flat space where there's nothing happening in the background. All right, does anybody want to ask any questions before I start doing some CFT? Awesome. All right, so as like any conformal field theory, and here I'm being a little bit sloppy, so experts will no doubt want to complain, but they can do that afterwards. If you look at conformal field theory, then you can always organize the spectrum into representations of this thing called the chiral algebra, or the vertex operator algebra. And so I want to define various types of conformal field theory based on the types of representations that appear. And so here's my rep theory. I want to ask two questions. Are all the representations completely reducible? Can I write them as direct sums of irreducibles? And how many irreducibles are there anyway? And so are there finitely many or not? So if there are finitely many irreducibles and everything can be written as a direct sum of irreducibles, we say that's a rational CFT. So the free fermionic string gives rise to a rational conformal field theory. Now, there are various ways of breaking that. So one of the most obvious ways is to say, well, yeah, everything's still completely reducible, but I have infinitely many irreducible representations. In that case, I will call it a non-rational conformal field theory, and the free bosonic string gives the standard example there. There are others, things like Liouville and possibly some others. I'm not really up to speed on these, but they're claimed to be non-rational in this sense. On the other side of the coin, we can have finitely many irreducibles, but we may lose the complete reducibility. There might be representations which can't be written as direct sums of irreducibles. And then we would speak about reducible but indecomposable representations. And with the finitely many irreducibles, some people call these log-rational conformal field theories. Symplectic fermions is our poster child here. If you haven't heard of those, don't worry, I'm not going to talk about them. And in the bottom right corner, we have the full-blown logarithmic CFTs. And the log here also stands for logarithmic, so most people would also refer to these as being logarithmic, but just for the sake of a partition, let me say here that you can have theories which have infinitely many irreducibles and representations which are reducible but indecomposable. In fact, these are probably most conformal field theories, in particular what some people call symplectic bosons, which is a fancy name for the bosonic ghost theory, which is probably more familiar to you. So these guys, full-blown logarithmic CFTs, life gets a bit hard, but also a little bit more interesting. I just asked the question, what type is the Nappi-Witten model? Well, the easiest way to start working on any conformal field theory is to identify the vacuum module. So this is where the chiral algebra is acting on itself. So we have the identity field, which is basically just acting as 1, multiplication by 1. And we have the generating fields of our chiral algebra. So remember in my Lie algebra, I had an E, an F, an I, and a J. So each of those gets promoted to a field of conformal dimension 1. And these are the affine fields which generate the affine symmetry of the Nappi-Witten conformal field theory. So there are many, many more fields descended from these. This sort of goes on. There's infinitely many of them. But I just want to give you a very, very brief painting of what this vacuum module looks like. So I said also that I and J function a bit like a Cartan subalgebra, and so the eigenvalues of the zero modes can be thought of as charges for the states of this theory. And so I can look at the I charge. So the I charge is in fact always 0 in the vacuum module. That's because I naught is central, and the I charge of the vacuum is of course 0. And then there's something which I would just call the J charge. You remember that the commutator of J with E was E and J with F was minus F. And so what that tells you is that every time you act with an E, you raise the J charge by 1, and every time you act with an F, you lower the J charge by 1. And of course, there's also the conformal dimension, which I'm going to draw increasing as we go down. All right, so you have a look at this vacuum module, and you realize with actually not too much work that there are absolutely no null states whatsoever, apart from 0, I suppose. But this module has no null states, and what this means is that you don't have any constraints on the spectrum of the conformal field theory. Right? So if you take any old representation of the affine version of our Nappi-Witten algebra H4, so if you affinize it and you look at its representations, they'll always be representations of the chiral algebra. So in particular, we can take the Verma modules, or if you prefer Fock spaces, whatever language you prefer, those will be representations of the chiral algebra. So that tells you immediately, because we have a carton with two types of charge, that we're going to have infinitely many irreducibles. Right? There's at least a two-parameter family of Verma modules. They're all representations of our chiral algebra. Right? So that means that rationality is off the table. We're either going to have a non-rational theory or we're going to have a logarithmic theory. One of the two. Now, in fact, formally, according to my definition, we know that it's going to be logarithmic because it's very easy to show that you get reducible but indecomposable Verma modules. A Verma module is always indecomposable, and all we need to do is find one which is reducible. And so, in fact, if we take the Verma module, which is sort of the parent of the vacuum module itself, so in other words, we take the generator to have I charge 0 and j charge 0, well, then you can check very easily from the commutation relations that you get an infinite string of singular vectors by acting with F0. So you start with the Verma vacuum, act with F0, you get a singular vector. Act with F0, you get another singular vector, and so on and so forth. So in fact, there are heaps of reducible but indecomposable Verma modules out there. Now, I've said that formally this means that Nappi-Witten is logarithmic, but it doesn't necessarily mean that, because when we're studying conformal field theory or even string theory, there's a bunch of consistency requirements. So just because these are representations of the chiral algebra doesn't necessarily mean that we have to take them as constituents of our spectrum. All right, so we don't actually know that this nasty looking thing here appears in the spectrum. We'd have to check various consistency conditions before we made any claims in that direction. Okay, so I'm not actually going to answer this question, even though I've tried to motivate it as something which is sort of interesting, at least to me. I'm not going to actually answer this question, is the Nappi-Witten model logarithmic for sure? I believe the answer is yes, and I think it's going to be fairly straightforward to check, but we didn't answer that question because we got bogged down with other things. But I do want to show you this main result. So the main result, first main result that I want to present is just the discussion of the representation theory of this Nappi-Witten chiral algebra. So we've got some Verma modules, and so I'm going to label them with their I charge and j charge of their vacuums. So Vij just means I and j are the eigenvalues of the zero modes of the carton. So it turns out that the Verma module is irreducible if and only if I is not an integer. And if I is an integer, then we can identify the maximal submodule precisely. So it's generated by a singular vector, and we can tell you what its j charge is, it's either this or this, and we can tell you its precise conformal weight. And because we can tell you this, that means we can write down not only the character of the Verma module, which is easy because it's freely generated, but we can also write down the character of its irreducible quotient. So I'm going to call irreducible quotients L, and you get some, nice looking, potentially formula for the character. And so these characters are useful because from these characters you build the partition function of your conformal field theory. So it's a very fundamental quantity. All right, a little bit about this main result. So I am not an expert on the physics literature, but I do know that in the mathematics literature, there's a paper by some colleagues, Chinese colleagues, Kaipo Zhang and two of her collaborators, where they study this precise question. And they seem to be able to establish this first point here. I don't believe that they were able to establish the second point but to be honest, I had a lot of difficulty actually understanding their paper. So they did have a theorem which essentially amounts to this first dot point. I couldn't understand their proof. It was split into 6 or 7 cases, and it was very long and complicated. Yeah, I kind of gave up, and so we decided to prove it ourselves. So Will has come up with a nice combinatorial proof, which doesn't involve many cases and is significantly shorter. I think it's a good one. And our proof also allows us to rigorously identify the maximal submodule of all of our Verma modules, which I think is necessary in order to get this character formula at the bottom. So there was a claim in the paper of Zhang and So, where they said something along the lines of there exist singular vectors if and only if some necessary and sufficient conditions are true. I believe in their proof they proved necessity. I don't think they proved sufficiency. And it turns out that when we looked at this with our proof methods, we found that their necessary and sufficient conditions were indeed sufficient, but they're also redundant in that they'd written 2 sets of conditions, and one of them you could show implied the other. So in any case, I think Will did a great job of cleaning up that, and I think he also extended it, and it's a very nice piece of work. I haven't found these character formulae in the physics literature anywhere, but if anybody has ever spied them, then I would appreciate knowing, because otherwise I'll probably get some unhappy reviewers who are going to complain at me. All right, so we have some information about highest weight modules, so Verma modules and their quotients, and that's really cool. But in the types of conformal field theories which we're looking at here, so these sort of logarithmic, non-rational, who knows, things like symplectic bosons, GL11, other theories which have similar representations. What we've learned from Hard Yakka is that there always seems to be a set of modules which I've been calling the standard modules of the conformal field theory. And if you can compute their characters, then you get a really nice modular basis for all the characters. So there's sort of some canonical set of representations that you should concentrate on. And it's usually pretty clear what these should be. And so in particular for our Nappi-Witten model, when I look at it, I say to myself, well, these standard modules are not going to be Verma modules. They're not going to be the irreducible quotients. They're going to be something more complicated, which we've been calling relaxed Verma modules. So they're like Verma modules, but you relax one of the conditions in their definition. And so instead of just having 2 parameters, I and j, they now have a 3rd parameter, which is the conformal dimension. So in our Verma modules above, the conformal dimension of the vacuum state was actually determined by I and j. And in the relaxed Verma modules, this is no longer the case. It becomes a free parameter all of its own. Now for experts, there's also a bunch of things called spectral flow automorphisms. And so technically, I don't want to just take my relaxed Verma modules. I want to take them and their images under spectral flow. I'm not going to talk about that any further. You can ask me about it later if you're interested. So what is a relaxed module, a relaxed Verma module? Well, essentially, when you take a highest weight module, what you do is you choose a raising operator and a lowering operator. So here we have our vacuum state, and you'll see that F0 is allowed to act on it freely and end up computing more and more excited states, but E0 is not, right? E0 annihilates this, so it's an annihilation operator for the purposes of this type of module, right? And then there are also positive modes like F1 and E1 and maybe I1 and J1 and all the rest, and they also annihilate. But the key feature here is that E0 annihilates the vacuum state. So in a relaxed module, what we do is we remove the annihilation by E0. So F0 is still allowed to act freely. It's allowed to do what it likes. But E0 now also is allowed to act freely, and it generates more and more excited states. We still have annihilation by positive modes like E1 and H. There's no H, E1 and J3 and F5. They still annihilate. but E naught is now a creation operator in some sense. Right, so that's a relaxed module. And you might think, well, that's a rather stupid thing to do, David. Why do you do that? Well, as I say, we have realized in many, many other examples that these things are absolutely essential.
So do you still have a well-defined vacuum state there? Is it still a unique vacuum state?
Well, we have a unique vacuum in the sense of the true vacuum. That's the one corresponding to the vacuum module up here. We still have this guy, but for the relaxed modules, instead of having a single vacuum state like we have here, now you have the countable infinity of them. There's kind of nothing you can do about that. It's an infinite degeneracy, but
is this like in the bosonic string you have some when you have beta gamma systems in the bosonic string you have some degeneracy that you can change with picture changing operators? Is this something like that?
The picture changing operators, I believe, correspond to spectral flow. So that's something different that I'm not talking about here. Okay. But you are correct that the beta gamma system, what I was calling symplectic bosons, have precisely these modules.
Cool, thank you.
And they are essential for understanding the conformal field theory. I don't know whether they're essential for understanding the gauge fixing of the string theory or the superstring theory, but you absolutely need them in the conformal field theory if you want a modular invariant partition function.
Oh, I see.
Yeah, nice stuff. All right, so as I've said here, the I and J charges fix the conformal dimension, and here the conformal dimension on the relaxed case is an independent quantity. So we have a 3-parameter family instead of a 2-parameter family. And so the relaxed guys outnumber the highest weight guys by an uncountable infinity to 1. So that's pretty cool. All right. So here's something which is rather neat. These relaxed modules form families where you can fix the I charge, you can fix the conformal dimension, but then you vary the J charge. And you might say that's a rather silly thing to do, but it's just an organizational thing, because when you move the J charge around, what you can see with some very simple calculations is that at some point you will pick a J, you can tune the value of J so that the module is going to be reducible but indecomposable, right? You have to have this. And so a simple cartoon to illustrate what's going on here is that we have our infinitely many ground states, this infinite degeneracy, and for most of them you can act with F naught and you can act with E naught and come back up, and here you can act with E naught and then act with F naught and get back to where you started. But there's sort of one place in which something weird happens. You can get from this state to this state with F naught, but you can't get back again with E naught. It's not possible to get back. And so that's maybe a little bit strange, but that's just the way representation theory works. And so what happens is that when you tune the J charge to this special value, the relaxed module degenerates into a highest weight module, which is this thing here, and something which looks like a highest weight module, except you've swapped the role of E naught and F naught. Right, so this guy here is not a highest weight module. We call that a conjugate highest weight module, just for want of a better term. So these relaxed modules are reducible but indecomposable, but in some sense they degenerate into highest weight modules and things that are almost highest weight modules. And so this is actually really important, because it means that if you understand the relaxed modules, then you actually understand the highest weight modules as well, because every highest weight module, modulo some spectral flow issues, can be understood as a degeneration of one of these relaxed modules. So relaxed modules are great. There's one more thing which you should probably realize fairly early on, is that when we look at these relaxed modules, here I mean a relaxed Verma module, but of course a Verma module might have some singular vectors. And in fact, it might have something which we call a relaxed singular vector. So it's very likely that instead of the relaxed Verma module being the irreducible, you might want to quotient, right? Set all of these singular vectors or relaxed singular vectors to 0. And so you can get irreducible relaxed modules. And instead of denoting them by R, which I think I was doing up here, there, R is for relaxed Verma, the irreducible quotients I'm just going to use an E. Don't ask me why I used E, I just did. All right, so now we have a whole bunch of new beasties to play with. And so you can say to Will, hey, Will, guess what? Your job now is to try to understand all of these relaxed Verma modules and their irreducible quotient. And so a couple of months later, he comes back with main result number 2, relaxed Verma module. Remember, I charge, J charge, and conformal dimension, all 3 parameters. He says that these Verma modules are going to be irreducible if and only if I is not an integer, or there's one more special case, if I happens to be 0 and the conformal weight is non-zero, then this guy is also irreducible. So this is relatively easy to prove. It was easier to prove than the standard Verma module case, but only because we could use the standard Verma module case. And this extra case here was a bit subtle, required a short argument. But yeah, it's not too bad. The nice thing about this is that we also have the maximal submodule. So if we take I to be an integer which is not 0, then the maximal submodule is generated by a relaxed singular vector. And we know its conformal dimension precisely, which means we can write down the character of the irreducible quotient precisely. It's not a very complicated character formula. Right? It's the character for the relaxed Verma, and to get the character of the irreducible quotient, you just get this extra factor out front. Right? So it's a very, very nice little result, I think. And, that's certainly, I'm pretty sure that that's new. All right. So I talked a bit about degenerations before. Still got a couple of minutes, so I'd like to just explain how this kind of all works, because this notion of degeneration also seems to be universal for many non-rational and or logarithmic conformal field theories. So remember I said that I claimed that these relaxed Verma modules were going to be my standard modules in some sense. So these guys, there's 3 parameters, and in order for these to be irreducible, we now know, thanks to main result number 2 and Will's hard work, that I can't be an integer. And it turns out that J also has to satisfy a constraint. All right, but it's, you know, it can't be this and it can't be that. So it's basically 3 parameters worth of freedom. All right, so these are my standard modules. And then we can degenerate. So we can degenerate by taking I to an integer, or we can degenerate by taking J to this ratio, conformal dimensions to I charge. All right, so let's do the first one first. So if we make I an integer, then it turns out that the relaxed Verma module develops a relaxed singular vectors, and we have identified the maximal submodule, and so we can find the irreducible quotient when I is an integer, but J is still not allowed to be this thing. All right, so once again, we get now essentially 2 parameters worth of freedom for these irreducibles. Alternatively, I can degenerate the second condition and keep the first. So if I force I to be not an integer, but J to satisfy one of these conditions, then the relaxed Verma degenerates, as we saw in this picture above, degenerates into a highest weight Verma and a conjugate highest weight Verma. And so I've ignored the conjugate highest weight Vermas because I can deal with those by spectral flow. And so I've just pictured this with a standard Verma module. So in this case, we again have just 1 parameter worth of excitement. J is, no, sorry, a 2 parameter family of Verma modules. So effectively, I, J are fixed, and these guys are all going to be reducible. And the last thing that I can do is I can impose both of these constraints, in which case I'm going to get the irreducible quotient of a Verma module. But I'll also get that that these here degenerate when I set J just right, and when they degenerate, you get a picture which looks exactly like this, but instead of getting a Verma module and a conjugate Verma module, you get an irreducible quotient and a conjugate of this. Right, so these guys here are our irreducibles when we take the I charge to be an integer and j satisfying this particular relation. So we have a complete understanding of how to get from standard modules down to irreducible highest weight modules and all the irreducible possibilities in between. Now, I should have said, I forgot to say at the start, that this degeneration pattern works when I is not zero. So the I charge being non-zero is sort of simplifying things a lot. When the I charge is equal to zero, there's some peculiarities. And so what happens, as I said before, that if the conformal dimension is not zero, then the relaxed Verma is already irreducible. So that's fine. And if it is zero, then it degenerates in a rather haphazard way. Instead of degenerating through a bunch of other irreducibles, it just degenerates all in one go. And you end up with the irreducible highest weight module with I equals zero. So here the conformal weight is necessarily going to be zero, and it looks a bit like this. So it's slightly different to this one here. All right, but that's it. Those are all of the irreducibles in our theory, modulo spectral flow. All right, so just to finish off, I want to reiterate, even though I motivated this by asking the question, is the Nappi-Witten model logarithmic? We haven't actually established that it is, and I think it's almost sure that what we'd really like to do in this world is actually say, here is a consistent physical spectrum, and then look inside that spectrum and extract reducible but indecomposable representations. So therefore establish that Nappi-Witten is indeed a logarithmic conformal field theory. Now, the route which I originally proposed to Will, by which we would start investigating this, was to take the characters which we've deduced and try to understand their modular transformations. So standard thing in conformal field theory is once you've got the irreducible characters, you apply modularity, and you should get some sort of closure. And, this part was actually done. It seemed to work, except that we kept getting contradictions every once in a while, and the contradictions were always happening when I was equal to zero. So in here, there's something which we really weren't understanding about the modularity. And so this part has not made it into the paper. It might be something we come back to in time if we get a better idea. But the path of modularity often also leads you to start considering the fusion rules of your conformal field theory. As you know, there's this thing called the Belinda formula. So if you understand the modular transformations of the characters, then you can probably get some information about the fusion rules. And it's probably reasonable to assume, historically, but also based on it's reasonable to guess that once you have fixed a reasonable spectrum of irreducible representations, such as these guys up here, now you can sit down and start fusing them together to see what other representations appear. So you can think of this in terms of channels in expansions of correlation functions. So you might take a 4-point function which involves primary fields or relaxed primary fields, if you like, corresponding to these irreducibles. But then when you insert OPEs, you get multiple channels, and sometimes those channels will give you logarithmic singularities. If that happens, what that means is that you have in the fusion product of your irreducibles, you will end up with a reducible but indecomposable representation of the Nappi-Witten chiral algebra. So that's kind of where one would look specifically to try to prove that what we have here is indeed a logarithmic CFT. All right, it's been a very long day. I thank you so much for paying attention, and yeah, I hope that we'll have many more interesting string theory talks next year. Thank you.
Well, thank you very much, David. Are there any questions? Okay, maybe I'll stop the recording.